Alright. Let's see, where do we leave off here? I guess I wanted to poke around some of these files. No labs repo. No. Do I have LA here? I'm going to add this. Shell. Was bash RC? Yeah. Okay. Data. It came with this open data PDF. Oh, there's a little PDF describing it. Maybe I should have read this first. Because I just implemented it based on the recitation video. I didn't realize there's instruction here. Alright, so Jesus Christ. Y'all are spamming the shit out of my chat this morning. Alright, or this afternoon. Gonna ban you, ban you, ban you. Please stop spamming. Alright, introduction. The purpose of this assignment is to become more familiar with bit level representation of integers and floating point numbers. I've achieved that, I think. You'll do this by solving a series of programming puzzles. Many of these puzzles are quite artificial, but you'll find yourself thinking much more about bits and working your way through them. Logistics. This is an individual project. All handouts are electronic. Clarifications and corrections will be posted on the course webpage. Handout instruction site specific. Insert a paragraph here that explains how okay. Start by copying blah blah. I don't really give a shit about this. The bits.c file contains a skeleton for each 13 programming puzzles. Your assignment is to complete each function skeleton using the straight line code. For the integer puzzles, I know loops or conditionals and limited number of C arithmetic and logical operators. Specifically, you're only allowed to use the following 8 operators. If you the functions further restrict the list. Also, you're not allowed to use any constants other than 8 bits. See the comments in bits.c for details. You already read that. Puzzles. This section describes the puzzles that you'll be solving in bits.c. Table 1 lists the puzzles in rough order of difficulty from easiest to hardest. The rating field gives difficulty rating, the number of points for the puzzle, and the max ops field gives the maximum number of operations you're allowed to use to implement each function. See the comments in bits.c for more details on desired behavior of the functions. You will also refer to bits.c. Okay. Okay, correctness, performance points, style points. Finally, we've reserved 5 points for a subjective evaluation of the style of your solutions and your commenting. Your solutions should be as clean and straightforward as possible. Your comments should be informative, but they need not be extensive. We already did all this. Beat the Prof contest. For fun, we're offering an official Beat the Prof contest that allows you to compete with other students and the instructor to develop the most efficient puzzles. The goal is to solve each data lab puzzle using the fewest number of operators. Students who match or beat the instructor's operator count for each puzzle are winners. To submit your entry to the contest type. So I will not be doing that. Alright, that was it. What else we got here? I want to look at btest.c. This thing is what, 500? Set jump. What the fuck does it use set jump for? This is all argument parsing. And it calls run test. What is this thing? Signal.h. Signal handler. This wires itself up. It wires a handler up to a signal number. And there's a timeout handler. There it goes, sig long jump to env buffer. And env buffer is set in main? No, in test function. It's a bit strange. Oh, because the while doesn't have a curly brace. Use get opt. I am tired, bro. That lunch really slowed me down. Alright. I don't think I need to read over all this. I'm capable of reading over it, but I'm not going to. I just want to get a good vibe for like how these things are being ran. There's a bunch of declarations for functions, for ratings. Basically, this is the data that drives the test. DLC. The hell is this? RM DLC. Make clean. Get status. Yeah, I mean the DLC program. It's just a compiled binary. It's a bummer. I like that they have a little Campbell in here for Perl scripts. Driver.pl. Wow. I have not seen Perl in ages. No functions or procedures. No socket stuff. Let's see what else is here. So you get driver lib PM, might be a compiled thing. No, just a Perl function. This thing uses sockets. There we go. So that was in the subroutine submit R. Rip grep submit R. Looks like it's only in driver lab. Driver lib submit R. Driver post. So that is in if you set nickname. So you can submit it if you set a nickname, but otherwise it doesn't seem to submit anything. That's the only socket used. What is this? Driver headers PM? Well, it seems kind of pointless. Why would you call it headers? Totally abuse this thing, try to exploit it, but that wouldn't be an ethical use of it. Okay. And then was test.c. Bunch of stuff to help them test the different functions. Check out. There we go. Okay. Just wanted to poke around a little bit. Done with the lab, so let's go ahead and move on to what is next. Well, we can read chapter 3, start doing the reading. We can watch chapter 3's lecture. We're going to investigate where the C programming thing came from. Because I don't see that in the lab's repo. Yeah, I don't see it here. And it might not be necessary because I've been doing a lot of C stuff. Depends how much of a review it is. CSAPP. And then we go to courses, down here, second to last, labs. So there's one in C programming. Auto lab. I don't see a C lab. I mean, I see it in the table here, but I do not see it anywhere else. Assignments. Oh, they used the Morgans. I didn't think about that. You have a different set of labs here. Oh, here it is. But there is no oh, there's a bit XOR. Okay. Okie dokie. So I don't think there is a C lab that I can actually get access to. Like this one. Where is it? Labs repo. Doesn't have it in it. And it isn't on the textbook website, which would be lab exercises here. So let's go ahead and vim up readme, and oh, this is in the labs repo. I'm just gonna kill that. Let's go back here, vim readme, and we're gonna delete C programming. So data, bomb, attack, buffer, architecture, cache, malloc, performance, shell, proxy, and then this SFS thing. It's not on the book's website, but if we go over to the course website, labs here, sorry, not lab machines, labs, there's this one here, SFS and C programming. Basically I can't find those, so they're gone. Bye. I think it might be worth tracking individual subsections. So 3.2 programming encodings, data formats, accessing information, arithmetic and logical operations, control, procedures, array allocation and access, heterogeneous data structures, combining control and data in machine programs, floating point code, and summary. And I will continue on with that once I get to those sections. Okay, let's start reading. So we're on the historical perspective. Oh, goody, we got a website already. I don't think that's right. Okay. We might have read this already. I'm not sure. All right, computers execute machine code sequences of bytes encoding the low-level operations that manipulate data, manage memory, read and write data on storage devices, and communicate over networks. A compiler generates machine code through a series of stages based on the rules of programming language, the instruction set of the target machine, and the conventions followed by operating system. The GCC compiler generates its output in the form of assembly code, a textual representation of the machine code, giving the individual instructions to in the program. GCC then invokes both an assembler and linker to generate the executable machine code from the assembly code. In this chapter, we will take a close look at machine code and its human-readable representation in assembly code. When programming in a high-level language like C, and even more so in Java, we are shielded from the detailed machine-level implementation of our program. In contrast, when writing programs in assembly code, as was done in the early days of computing, a programmer must specify the low-level instructions the program uses to carry out computation. Most of the time, it is much more productive and reliable to work at a higher level of abstraction provided by a high-level language. The type checking provided by a compiler helps detect many program errors and makes sure we reference and manipulate data in consistent ways. With modern optimizing compilers, generated code is usually at least as efficient as what a skilled assembly language programmer would write by hand. Best of all, a program written in a high-level language can be compiled and executed on a number of different machines, whereas assembly code is highly machine-specific. So why should we spend our time learning machine code? Even though compilers do most of the work in generated assembly code, being able to read and understand it as an important skill for serious programmers. By invoking the compiler with appropriate command line parameters, the compiler will generate a file showing its output in assembly code form. By reading this code, we can understand the optimization capabilities of the compiler and analyze the underlying inefficiencies in the code. As we will experience in Chapter 5, programmers seeking to maximize the performance of a critical section of code often try different variations of the source code, each time compiling and examining generated assembly code to get a sense of how efficiently the program will run. Furthermore, there are times when the layer of abstraction provided by a high-level language hides information about the runtime behavior of a program that we need to understand. For example, when writing concurrent programs using a thread package, as covered in Chapter 12, it is important to understand how program data are shared or kept private by the different threads, and precisely how and where shared data are kept private by, sorry, I need to read my bookmark here. It is important to understand how program data are shared or kept private by the different threads, and precisely how and where shared data are accessed. Such information is visible at the machine code level. As another example, many of the ways programs can be attacked, allowing malware to infest a system involves nuances of the ways programs store their runtime control information. Many attacks involve exploiting weaknesses in systems programs to overwrite information and thereby take control of the system. Understanding how these vulnerabilities arise and how to guard against them requires a knowledge of the machine level representation of programs, the need for programmers to learn. Machine code is shifted over the years from one of being able to write programs directly in assembly code to one of being able to read and understand code generated by compilers. In this chapter, we will learn the details of one particular assembly language and see how C programs get compiled into this form of machine code. Reading the assembly code generated by a compiler involves a different set of skills than writing assembly code by hand. We must understand the transformations typical compilers make in converting the constructs of C into machine code. Relative to the computations expressed in the C code, optimizing compiler can rearrange execution order, eliminate unneeded computations, replace slow operations with faster ones, and even change recursive computations into iterative ones. It's worth rereading. Relative to the computations expressed in the C code, optimizing compilers can rearrange execution order, eliminate unneeded computations, replace slow operations with faster ones, and even change recursive computations into iterative ones. Understanding the relation between source code and the generated assembly can often be a challenge. It's like putting together a puzzle having a slightly different design than the picture on the box. It is a form of reverse engineering, trying to understand the process by which a system was created by studying the system and working backwards. In this case, a system is a machine-generated assembly language program rather than something designed by a human. This simplifies the task of reverse engineering because the generated code follows fairly regular patterns, and we can run experiments having the compiler generate code for many different programs. In our presentation, we give many examples that provide a number of exercises illustrating different aspects of assembly language and compilers. This is a subject where mastering the details is a prerequisite to understanding the deeper and more fundamental concepts. Those who say, I understand, am I on the right page here? Yeah, those who say, I understand the general principles, I don't want to bother learning the details, are deluding themselves. Highlighting that. It is critical for you to spend time studying the examples, working through the exercises, and checking your solutions with those provided. Our presentation is based on x86-64, the machine language for most of the processors found in today's laptop and desktop machines, as well as those that power very large data centers and supercomputers. This language has evolved over a long history, starting with Intel Corporation's first 16-bit processor in 1978, through to the expansion to 32 bits. And most recently to 64 bits. Along the way, features have been added to make it better use of the available semiconductor technology and to satisfy the demands of the marketplace. Much of the development has been driven by Intel, but its rival AMD has also made important contributions. The result is a rather peculiar design with features that make sense only when viewed from a historical perspective. It is also laden with features providing backwards compatibility that are not. Let me turn a light on here. Actually, I'll get my reading light going on here. That'll help. There we go. Turn that off. Also laden with features providing backwards compatibility that are not used by modern compilers and operating systems. We will focus on the subject of the features used by GCC and Linux. This allows us to avoid much of the complexity and many of the arcane features of x86-64. Our technical presentation starts with a quick tour to show the relationship between C assembly code and machine code. We then proceed to the details of x86-64, starting with the representation and manipulation of data and the implementation of control. We see how control constructs in C, such as if, while, and switch statements are implemented. We then cover the implementation of procedures, including how the program maintains a runtime stack to support the passing of data and control between procedures, as well as storage for local variables. Next, we consider how data structures such as array structures and unions are implemented at a machine level With this background in machine level programming, we can examine the problems of out of bounds memory references and the vulnerability of systems to buffer overflow attacks. We finished this part of the presentation with some tips on use of GDB debugger for examining the runtime behavior of machine level program. The chapter concludes with a presentation on machine program representations of code involving floating point data and operations. The computer industry has recently made the transition from 32 to 64-bit machines. A 32-bit, not recently at this point, a 32-bit machine can only make use of around 4 gigabytes of random access memory, while with memory prices dropping at dramatic rates, definitely not right now, and our computational demands and data sizes increasing, it has become both economically feasible and technically desirable to go beyond this limitation. Current 64-bit machines can use up to 256 terabytes of memory and could readily be extended to use up to 16 exabytes. Although it is hard to imagine having a machine with that much memory, keep in mind that 4 gigabytes seemed like an extreme amount of memory when 32-bit machines became commonplace in 1970s and 1980s. Our presentation focuses on the type of machine level programs generated when compiling C and similar programming languages targeting modern operating systems. As a consequence, we make no attempt to describe many of the features of x86-64 that arise out of its legacy support for the styles of programs written in the early days of microprocessors, when much of the code was written manually and where programmers had to struggle with the limited range of addresses allowed by 16-bit machines. There's a website here. Maybe go and pull that up, see if we want to do it. CSAPP, websites, IA30. Okay, so you got some registers, some stuff going on here. Illustration of the stack. I'm down for this. Yeah, this is good. We'll come back to this though, because this historical perspective shouldn't take too long. Let's just verify that the website is repeating itself here. It doesn't really. Okay, I'll go ahead and read I'll read the website up here, and then I'll do it later. So, Intel Architecture 32, the 32-bit processor predecessor to x86-64, was introduced by Intel in 1985. It served as the machine language of choice for several decades. Most x86 microprocessors today and most operating systems installed in these machines are designed to run x86-64. However, they can also execute Intel Architecture 32 programs in a backwards compatibility mode. As a result, many application programs are still based on Intel Architecture 32. In addition, many existing systems cannot execute x86-64 due to limitations of their hardware or system software. Intel Architecture 32 continues to be an important machine language. If you find that having a background in x86-64 will enable you to learn IA32 machine language quite readily. Okay, great. All right, a historical perspective. The Intel processor line, colloquially referred to as x86, has followed a long evolutionary development. It started with one of the first single-chip 16-bit microprocessors, where many companies It started with one of the first single-chip 16-bit microprocessors, where many compromises had to be made due to the limited capabilities of integrated circuit technology at the time. Since then, it has grown to take advantage of technology improvements, as well as to satisfy the demands for higher performance and for supporting more advanced operating systems. The list that follows shows some models of Intel processors and some of their key features, especially those affecting machine-level programming. We use the number of transistors required to implement the processors as an indication of how they have evolved in complexity. In this table, K denotes 1,000, M denotes 1 million, and G denotes 1 billion. That's just a bunch of processors. 8086, the OG. One of the first single chip 16-bit microprocessors, the 8088 variant of the 8086 with an 8-bit external bus, formed the heart of the original IBM personal computers. IBM contracted with then tiny Microsoft to develop the MS-DOS operating system. The original models came with 32,768 bytes of memory and 2 floppy drives, no hard drive. Architecturally, the machines were limited to 655,360 byte address space. Addresses were only 20 bits long, so 16-bit architecture, but addresses are 20 bits long. Interesting. And the operating system reserved 393,000 bytes for its own use. In 1980, Intel introduced the 8087 floating point coprocessor. 45K transistors to operate alongside the 8086 and 8088 processor. Executing the floating point instructions, the 8087 established a floating point model for the x86 line, often referred to as x87. Okay, 8286, which has about 130,000 transistors, added more and now obsolete addressing modes, formed the basis of the IBM PC-AT personal computer, the original platform for MS Windows. i386, 275,000 transistors, expanded the architecture to 32 bits, added the flat addressing model used by Linux and recent versions of the Windows operating system. It's the first machine in the series that could fully support a Unix operating system. i486, improved performance and integrated the floating point unit into the processor chip, but did not significantly change the instruction set. Pentium, this was a big craze when I was a young kid, which is the 586. So it went 386, 486, 586. Pentium. Improved performance, but only added minor extensions to the instruction set. Pentium Pro is for introduce a radically new processor design, internally known as the P6 microarchitecture. Add a class of conditional move instructions to the instruction set. Pentium MMX added a new class of instructions to the Pentium processor for manipulating vectors of integers. Each datum can be 1, 2, 4 bytes long. Each vector totals 64 bits. So this is kind of like SIMD before SIMD. Continuation of the P6 microarchitecture. It's Pentium 2, Pentium 3. Introduce SSE, a class of instructions for manipulating vectors of integers or floating point data. Each datum can be 1, 2, or 4 bytes packed into vectors of 64 bits. Of 128 bits. Later versions of this chip went up to 24 million transistors due to the incorporation of the level 2 cache on the chip. Pentium 4 extended SSE to SSE2, added new data types including double precision floating point, along with 144 new instructions for these formats. With these extensions, compilers can use SSE instructions rather than x87 instructions to compile floating point code. So Pentium 4 is pretty important at 42 million transistors. Pentium 4E added hyperthreading. Okay. Symmetric multithreading. A method to run 2 programs simultaneously on a single processor, as well as EM64T, Intel's implementation of a 64-bit extension to IA32 developed by Advanced Micro Devices, which we refer to as XA664. Core 2 returned to a microarchitecture similar to P6, first multi-core Intel microprocessor, where multiple processors are implemented on a single chip. So it's 2006, yep. I remember that. Did not support hyperthreading. Core i7. So we're at about 781 million transistors, incorporated both hyperthreading and multi-core. I mean, these aren't insane numbers. I mean, you started at like 69,000 transistors. That's not a lot of transistors for a whole chip, even though it's 16-bit, had a lot of limitations. But something that I would recognize is like a modern chip, i386, only 275,000 transistors. So the Core i7 incorporated both hyperthreading and multi-core, with the initial version supporting 2 executing programs on each core and up to 4 cores on each chip. Sandy Bridge, we're now in the billions of transistors. Introduced AVX, an extension to the SSD to support data packed into 256-bit vectors. I don't think AMD supports AVX. Or is it AVX 512? Does AMD support AVX? If so, what versions? Yeah, it's the 512 support they didn't implement. AVX 2 is on Xenon later. What happens if you run a program on a machine that has AVX 512 instructions, but the chip doesn't support them? I imagine it's a like SIG illegal instruction. Yeah, it's a signal. High performance softwares like BLAS, game engines, compression libraries does runtime CPU ID detection, dispatches to the best implementation available. Okay. So it's like, okay, do you support 512? Then we're going to do the 512 thing, obviously. So most vectorization is done with runtime conditional checks. What about auto vectorization? No, most vectorization is not done with runtime checks. Auto vectorization usually targets fixed ISA at compile time. Runtime dispatch is used when you want one binary to support multiple CPUs. Say I compile my program with AVX2, like in your example. Two questions. One, is there metadata in the ELF binary that tells the OS not to even run the program if AVX2 is not supported on that machine? Two, does GCC do some sort of allow some sort of check for AVX2 at initialization before main is called to avoid getting a runtime sig ill at a later time? No, not in normal Linux binaries. If you compile with MAVX2, resulting ELF binary does not contain a requires AVX2 flag. The Linux kernel does not check CPU feature compatibility before execution. The loader LD Linux does not check either. The OS will happily start your program. It only crashes when the CPU encounters a first unsupported instruction. Why doesn't ELF encode this? ELF has ISA level, ABI info, relocations, dynamic, but x86 feature bits are not part of the ELF compatibility model. That's a bummer. Unlike ARM, which uses different ELF machine flags for Neon, etc. x86 assumes the binary knows what it's doing. Attribute constructor, built-in CPU supports. That's pretty cool. Okay. It's interesting. All right, let's continue reading. So the Sandy Bridge introduced AVX, an extension to SSE, to support data packed into 256-bit vectors. And then Haswell extended AVX to AVX2, adding more instructions and instruction formats. And then there's AVX 512, which Intel mainly supports, and AMD doesn't. Each successive processor has been designed to be backwards compatible to run code compiled for an earlier version. As we will see, there are many strange artifacts in the instruction set due to this evolutionary heritage. Intel has had several names for the processor lines, including IA32 for Intel Architecture 32-bit, and most recently Intel 64, the 64-bit extension to IA32, which we will refer to as x86 64 or AMD 64. We will refer to the overall line by the commonly used colloquial name x86, reflecting the processor name conventions up through the i486. I thought the 386 was the first one. Anyways, over the years, several companies have produced processors that are compatible with Intel processors, capable of running the exact same machine-level programs. Chief among them is AMD. For years, AMD lagged just behind Intel in technology, forcing the market strategy where they produced processors that were less expensive, although somewhat lower in performance. They became more competitive around 2002, being the first to break the 1 gigahertz clock speed barrier for a commercially available microprocessor and introducing x86 64, the widely adopted 64-bit extension to Intel's IA32. Although we will talk about Intel processors, our presentation holds just as well for the compatible processors produced by Intel's rivals. Much of the complexity of x86 is not of a concern to those interested in programs for the Linux operating system and generated by the GCC compiler. The memory model provided in the original 8086 and its extensions in the 8286 became obsolete with the i386. The original x87 floating point instructions became obsolete. So talking about the complexity that's become obsolete. The memory model provided in the original 8086 and the extension to the 8286 became obsolete with the i386. The original x87 floating point instructions became obsolete with the introduction of SSE2, although we still see vestiges of the historical evolution of x86 to x86 64-bit programs. Many of the most arcane features of x86 do not appear. Until microprocessor complexity. Just number of transistors going up over the years, decades. If we plot the number of transistors in the different Intel processors versus the year of introduction and use a logarithm scale for the y-axis, we can see that the growth has been phenomenal. Fitting a line through the data, we see that the number of transistors increases at an annual rate approximately 37%, meaning that the number of transistors doubles about every 26 months. This growth has been sustained over multiple decades. The history of x86 microprocessors. In 1965, Gordon Moore, a founder of Intel Corporation, extrapolated from the chip technology of the day, by which they could fabricate circuits with around 64 transistors on a single chip, to predict that the number of transistors per chip would double every year for the next 10 years. His prediction became known as Moore's Law. As it turns out, his prediction was just a little bit optimistic, but also too short-sighted. Over more than 50 years, the semiconductor industry has been able to double transistor count on average every 18 months. Similar exponential growth rates have occurred for the other aspects of computer technology, including the storage capacities of magnetic disks and semiconductor memories. These remarkable growth rates have been the major driving forces of the computer revolution. Program encoding. Suppose we write a C program as two files, p1.c and p2.c. We can then compile them using code, using a Unix command line, blah, blah. The command, so the command is gcc optimize g, output to p, p1, and p2. The command gcc indicates the GCC compiler, C compiler. Since this is a default compiler on Linux, we could also invoke it as simply cc. I can't do that on. It says, nope. Oh, I can. Stat. If we read link. I've never seen, okay, that makes sense. There's a user bin GCC then. User bin GCC. Yeah, okay. The command GCC invokes the GNU C compiler, or the GCC C compiler. This is the default on Linux. We could also simply invoke it as CC. Command line option -OG, I think it's for debugging. This optimization level was introduced in GCC version 4.8. Early version GCC, as well as non-GNU C compilers, will not recognize this option. For these, using optimization level 1, specified with the command line flag 01, is probably the best choice for generating code that follows the original program structure. That flag instructs the compiler to apply a level of optimization that yields machine code that follows the overall structure of the original C code. Invoking higher levels of optimization can generate code that is so heavily transformed that the relationship between the generated machine code and the original source code is difficult to understand. We will therefore use optimize G optimization as a learning tool and then see what happens as we increase the level of optimization. In practice, higher levels of optimization, e.g. specified with option 01 or 02, are considered a better choice in terms of the resulting program performance. The GCC command invokes an entire sequence of programs to turn the source code into executable. First, the C preprocessor expands the source code to include any files specified with the #include commands and to expand any macros specified with #define declarations. Second, the compiler generates assembly code versions of the two source files having names p1.s and p2.s. Next, the assembler converts the assembly code into binary object code files p1.o and p2.o. Object code is one form of machine code. It contains binary representation of all of the instructions, but the addresses of global values are not yet filled in. Finally, the linker merges these two object code files along with code implementing library functions, e.g. printf, and generates the final executable code file P as specified by the command line directive -op. Executable code is the second form of machine code we will consider. It is the exact form of code that is executed by the processor. The relation between these different forms of machine code and the linking process is described in more detail in Chapter 7. Can't wait to get to that. So, machine level code. As described in Section 139, computer systems employ several different forms of abstraction, hiding details of implementation through the use of simpler abstract model. Two of these are especially important for machine level programming. First, the format and behavior of a machine-level program is defined by the instruction set architecture, or ISA, defining the processor state, the format of the instruction, and the effect of each of these instructions will have on the state. Most ISAs, including x86-64, describe the behavior of a program as if each instruction is executed in sequence, with one instruction completing before the next one begins. The processor hardware is far more elaborate, executing many instructions concurrently, but it employs safeguards to ensure that the overall behavior matches the sequential operation directed by the ISA. So the ISA is the interface to the programmer. But yeah, the ISA is an abstraction. And like any abstraction, it has holes. And those holes would include things like when speculative execution bugs out, there's performance issues, just, with like cache access, things like Spectre and Meltdown. Like, basically, the machine is the machine. It's presenting an abstract interface for you to compile and target, and write your own assembly code for. But that abstraction, while it is the contract, it's not the actual behavior. Yeah, it's just an interface. All right. Second, the memory address used by a machine-level program are virtual addresses, providing a memory model that appears to be a very large byte array. The actual implementation of memory system involves the combination of multiple hardware memories and operating system software as described in Chapter 9. The compiler does most of the work in the overall compilation sequence, transforming programs expressed in a relatively abstract execution model provided by C into the very elementary instructions that the processor executes. The assembly code represented is very close to machine code. Its main feature is that it is more readable than readable textual format as compared to binary format of the machine code. Being able to understand assembly code and how it relates to the original C code is a key step in understanding how computers execute programs. The machine code for x86-64 differs greatly from the original C code. Parts of the processor state are visible that normally are hidden from the C programmer. So the program counter, commonly referred to as the PC and called the RIP in x86-64, RIP, indicates the address and memory of the next instruction to be executed. The integer register file contains 16 named locations storing 64-bit values. These registers can hold addresses corresponding to C pointers or integer data. Some registers are used to keep track of critical parts of the program state, while others are used to hold temporary data such as arguments and local variables for a procedure, as well as the value to be returned by a function. The conditional code registers hold status information about the most recently executed arithmetic or logical instruction. These are used to implement conditional changes in the control or data flow, such as is required to implement if and while statements. A set of vector registers can each hold one or more integer or floating point values. So you got your register file, which is like your normal registers. You got your vector registers. I think you also have like floating point registers that are included in this list. I would also consider the instruction pointer as another register because you can assign into it. It doesn't seem any special outside of that. It's the register used to point to where the code is being fetched from. Whereas C provides a model in which the objects of different data types can be declared and allocated in memory, machine code views the memory as simply a large byte addressable array. Aggregate data types such as arrays and structures are represented in machine code as contiguous collections of bytes. Even for scalar data types, assembly code makes no distinction between signed or unsigned integers. I guess for the arithmetic it's the same. Okay. Maybe it doesn't. Okay. between different types of pointers, or even between pointers and integers. Yeah. The program memory contains the executable machine code. I'm going to highlight this. The program memory contains the executable machine code for the program, some information required by the operating system, a runtime stack for managing procedure calls and returns, and blocks of memory allocated by the user. Using the malloc function, as mentioned earlier, the program memory is addressed using virtual addresses. At any given time, only limited subranges of virtual addresses are considered valid. For example, x86-64 virtual addresses are represented by 64-bit words. In current implementation of these machines, the upper 16 bits must be set to 0. So that's 2, 60, 50, 48. Yeah, 48 to the power of 48. And so an address can potentially specify a byte range of 2 to the 48 or 64 terabytes. I think I showed that it was 49 recently. More typical programs will only have access to a few megabytes or perhaps several gigabytes. The operating system manages this virtual address space, translating virtual addresses to physical addresses of values in the actual processor memory. A single machine instruction performs only a very elementary operation. For example, it might add 2 numbers stored in registers, transfer data between memory and a register, or conditionally branch to a new instruction address. The compiler must generate sequences of such instructions to implement program constructs such as arithmetic expression evaluation loops or procedure calls and returns. Aside, the ever-changing forms of generated code. In our presentation, we will show code generated by a particular version of GCC with particular settings of the command line options. If you compile code on your own machine, chances are you will be using a different compiler or a different version of GCC and hence will generate different code. The open source community supporting GCC keeps changing the code generator, attempting to generate more efficient code according to changing code guidelines provided by the microprocessor manufacturers. Our goal in studying these examples shown in our presentation is to demonstrate how to examine assembly code and map it back to constructs found in higher level languages. You will need to adapt these techniques to the style of code generated by your particular compiler. Godbolt does a really good job at this, but we're going to learn how to do it ourselves. Code examples. Suppose we write a C code file mstore.c containing the following function definition. So you got a long mult to long, and we got a mult store, which multiplies and stores the value. Makes sense. You can do that in a single instruction. To see the assembly code generated by the C compiler, we can use the -s command line option. Okay, let's go ahead and write this out. I'm pretty sure this can compile into a single assembly instruction though. Yeah, let's just pull this down, move this over here, pull that up there. Actually, move this guy over here, there you go. Let's go ahead and make dir chapter 03, copy chapter 02. I want the get ignore and the make file. Chapter 03. What else do I want? I think everything else is fine. CD into there. Oops. I'm pretty sure I added this thing. There we go. Okay, well we can just delete all this. That's fine. Okay. And then here, I want to do vim test. What was this? Mult store or mstore.c. And here we're gonna have long mult2. Long. Wait a minute. Please go away. Go away. Long That's just a declaration. And then here we have void mult store, long X, long Y, long destination. And then here we have long T is equal to mult 2 of X and Y. And we're going to assign in to destination T. Okay. And then I want to just do object code on this. Or I guess it's going to generate assembly. So if we do makefile, build mult, what is it called? Mult mstore.s, and so take an mstore.c, and then what if we can use zigcc? We'll do og -s. I don't think I need that. Okay. User defined symbol mult2 mstore. Yeah, what's wrong with that? Mult2. Oh, they're both doing that. Okay. Alright, then makefile. Huh? We'll just do a makedir then. Oh, this needs to be a phony. Shit. Zig did not like the dash C. What is this? Argument unused during compilation. Dash. There is no dash C, dude. There's dash G. The hell? Where's Ask AI? I'll just ignore it. It's fine. Where the fuck's that the book goes? None of the debugging stuff that I have. So maybe we fix that. Say, hey, it says OG S and then output. There we go. A lot simpler. So we got our multi-store label. it inlines. Oh no, it doesn't have the mult2, so it just does call mult2 at the PLT. Okay, it's a good clang. Oh, it has nice little comments too. Begin function multi-store. Type information. What is this fake use? RBX, RSI, RDI. Well, it is saying that it's still calling it. Let's open up the last of these, which is Zig. Good Lord, Ziggy boy. It's a lot. Build OBJ. Okay, let's continue reading. So we run our GCC to generate the assembly. This will cause GCC to run a compiler, generate an assembly file in msort.s and go no further. Normally, when it would then invoke the assembler to generate an object code file. The assembly code file contains various declarations, including the following set of lines. The multi-store push quad word RBX. And then we actually, let's pull up the, can I just like put you down at the bottom? Yeah. Build mstore.gcc. There's a push queue or move quad word RDX into RBX. Call the mult2 at PLT REX to RBX. That's the assignment into the effective address that's stored in RBX. And then pop quad word RBX. So it reassigns the last element in the stack into RBX, the previous version of RBX. And then return. explain the binary object code for a program, say mstore, we use a disassembler described below to determine that the code for the procedure is 14 bytes long. We then use GNU debugging tool on mstore.o to give it the command and give it the command x14xb multistore or multstore. Type display abbreviated x 14 hexadecimal hex formatted also x bytes starting at the address where the function multstore is located. You'll find that GDB has many useful features for analyzing machine level programs, as will be discussed in section 3.10.2. Okay, I'm going to take a little bit of a break here. What time is it? 4:30ish. I'm going to take a break here for maybe about 30 minutes or so. Maybe I'll get something to eat. But my brain's not wanting to read this right now. So instead of pushing forward, I'm just going to take a break, come back. Cool. I'll be back in probably about 30.